Uh, okay. So, uh, so this week I'll be discussing questions from week two classes. So I have prepared some questions, and we'll be discussing those questions today. So the first question is given like this. Let fxy equals to y time x square minus y square divided by x square plus y square when xy is non-zero and 0 when xy is 0. Then calculate the value of fy00. Okay, so solution. Now, since we already know the definition of the partial derivative of y at the point 0, 0, so then we can just simply put the definition, just write the definition and then put all the values. So fy00 is nothing but limit k tends to 0, f of 0 comma k minus f of 0 comma 0 divided by k. So now from the above function we can see that sorry, limit k tends to 0 and f of 0 comma k is nothing but k times 0 square minus k square divided by uh, s- uh, 0 square plus k square divided by k minus 0. So this is same as limit k tends to 0 minus of k cube divided by k cube, and which is negative of minus 1. I mean negative of 1. So fy of 0 comma 0 is nothing but negative 1. So this is the answer of the first question. Okay, so now let us go to the next question, if there is no doubt. Question number 2. Let fxy equals to e to the power minus x sine of x plus y. Then what will be the value of del f del y minus del f del x? So now from here, see that both the partial derivative with respect to y and with respect to x exist. So similarly, so simply we can just find out the derivative with respect to y first. So which is nothing but e to the minus x cos of x plus y. And similarly, the derivative with respect to x is nothing but the partial derivative with respect to x is nothing but minus e to the power minus x sine of x plus y plus e to the power minus x cos of x plus y. Okay, so now just substitute all the value here. Del f del y minus del f del x is nothing but e to the power minus x cos of x plus y. So negative negative positive minus x sine of x plus y minus e to the power minus x cos of x plus y. Now these two get cancelled out. So we are left with e to the power minus x sine of x plus y, which is nothing but f. So fy minus fx is nothing but f. And this is the answer. Okay. So this is very easy. So you just do the derivative first with respect to the y variable, which is the partial derivative with respect to y, and then partial derivative with respect to x. And then you just substitute all the value of the partial derivative of y and x, and then just do some simple calculation. And you'll find out that f y minus f of x is nothing but the f we considered in the beginning. So this is our answer. Okay. So now we're gonna go to the next question. Question number 3. And it says that let u equals to e to the power x square plus y square. Then find the value of x del u del x plus y del u del y. Okay. So now this question is also very simple because here you use a function of two variable x and y. So del u del x is nothing but e to the power x square plus y square into the derivative of x square plus y square with respect to x, and this is nothing but e to the power x square plus y square into 2x, because the derivative of y square will be 0 with respect to the x variable. Now similarly, del u del y is nothing but exponential x square plus y square into del y x square plus y square. So this will be same as e to the power x square plus y square. And now with the partial derivative of y with respect to the partial derivative of y of x square plus y square will be 2y, because the derivative of x square with respect to y will be 0. So now we just substitute the values. Then x del u del x plus y del u del y, and this is nothing but 2 times x square into exponential x square plus y square plus 2 times y square into exponential x square plus y square. So this is 2 times x square plus y square exponential x square plus y square. So if you just take u equals to exponential x square plus y square, then ln of u is nothing but simply x square plus y square into ln e, which is nothing but x square plus y square, as ln of e is 1. So this is nothing but 2 times ln of u into u. So this is our answer. Hence x del u del x plus y del u del y, this is same as 2u ln of u. Okay, so this is the answer of our next question. So I think this was question number 3. So yeah, please go through the solution again, and if you have any doubts, then you see the video again, and also you see the notes, and then again if you have any doubts, then you ask me in the next class. So this was the answer. Now we're going to go to the next question, which is question number 4. So let fxy equals to x cube plus 2x to the power 3 by 2 into y to the power alpha minus 3x to the power beta into y to the power 5 by 2 be a homogeneous function of order 3. Then what is the value of alpha plus beta? Okay, so a function is given such that f of x like f of x comma y equals to x cube plus 2x to the power 3 by 2 into y to the power alpha minus 3x to the power beta into y to the power 5 by 2, which is an homogeneous function of order 3. So then they're asking that what will be the value of alpha plus beta. Now, before solving this question, we have to know what is the definition of homogeneous function of any order which is a positive integer. So first we're gonna write the definition of a homogeneous function and then we'll solve the question. So just write now the definition of homogeneous function. So let f from parent to R be a real valued function. Then we say f is homogeneous of degree alpha if f of lambda x equals to lambda to the power alpha f of x, where x is in Rn and lambda is in R. Okay, so x is in Rn means x looks like this. So this is an nth tuple where each xi is a real number. Okay, so now let us see an example of homogeneous function. So consider this function. So now f is a function from R2 to R, so that means n is 2 here. So now you see that f of lambda x comma lambda y, this is same as lambda x square. So this is lambda x square x square. So this is lambda square time f of x comma y. So here alpha is 2. Hence f is a homogeneous function of order 2. Okay. So now I hope this definition is clear. So we can give another example. For example, so yeah, let us just write this example. So just take f of x comma y equals to x. This is also a function from R2 to R. N is 2, dimension is 2. Then simply f of lambda x comma lambda y is nothing but lambda of x, which is lambda of f of x comma y. So here f is a homogeneous function of order 1. Okay, because this is same as sorry, because here alpha is 1. So that's why. So now come to the question. So in the question, they have given that f is a homogeneous function of order 3. So that means uh, so given that f is a homogeneous function of order 3. So now since f is a homogeneous function of order 3, this implies that f of lambda x comma lambda y, this will be same as lambda q times f of x comma y. Now f of lambda x comma lambda y, uh, this is nothing but lambda x whole cube plus 2 times lambda x to the power 3 by 2 into y to the power alpha plus, sorry, minus 3 times lambda x to the power beta into, so this will be lambda y to the power 5 by 2. Okay, and this is same as lambda q x cube plus 2 lambda to the power 3 by 2 into alpha, 3 by 2 plus alpha into x to the power 3 by 2 into the y to the power alpha minus 3 lambda time lambda to the power beta plus 5 by 2 into x to the power beta into y to the power 5 by 2. Okay, so this is our f of lambda x comma lambda y, and lambda cube times f of x comma y is nothing but lambda cube uh, x cube plus lambda cube 2 lambda cube x to the power 3 by 2 y to the power alpha minus 3 lambda cube x to the power beta y to the power 5 by 2. Now since f of lambda x comma lambda y is lambda cube f of x comma y, so this will imply that we have to compare these two. Uh, these two. So now if we compare these two equation, then we can see that that this powers can be compared. So this power will be equals to this power, and this power will be equals to this power. So this is implying that 3 by 2 plus alpha equals to 3, and beta plus 5 by 2 equals to 3. So this implies alpha equals to 3 minus 3 by 2, which is 3 by 2, and beta equals to 3 minus 5 by 2, which is 1 by 2. So alpha plus beta is 3 by 2 plus 1 by 2, which is 4 by 2, which is 2. So the answer is 2. Hence alpha plus beta is 2. So this is the answer of our question. So yeah, kindly go through the answer again. So in the question, it was given that if it's a homogeneous function of order 3, then we have to find the sum of alpha plus beta. So since it's a homogeneous function of order 3, so we can just simply say that f of lambda x comma lambda y equals to lambda q times f of x comma y. Then we just substitute the values of f of lambda x comma lambda y and f of x comma y, and then we compare the power of lambda on both side of on both side. So now if you just compare, then we can see that two equations are coming, which is 3 by 2 plus alpha equals to 3 and beta plus 5 by 2 equals to 3. Now if you solve these two equations, we will get alpha equals to 3 by 2 and beta equals to 1 by 2. So this is implying that alpha plus beta is 2, and this is our answer. So I hope this is clear. Now if this is clear, then we're gonna go to the next question. Okay, so this is question number 5. So it is given that, so let fx 0 0 and if y 0 0 is 0, if x 0 y is y, and if y x 0 is x square, then what is the value of fxy plus fyx at 0 comma 0? Okay. Okay, just come to the solution. So now in the question, it is given that both the partial derivative of fx and fy at the point 0 comma 0 is 0, and fx 0 y is y, and fy x 0 is x square. So then they are asking us the question that what is the value of the mixed partial derivative of fxy plus fyx at 0 comma 0. Now this fxy and fyx are nothing but the second order mixed partial derivatives. Okay. So okay. So now before solving this question, uh, I'm going to write the definitions of both fxy and fyx first. So so see that del square f by del x del y, this is same as doing the partial derivative with respect to x to the function del f del y, correct? And this is also written as f of y. Now since we are doing the partial derivative of x of the function fy, so sometimes this is written like fy of x or simply fyx. Similarly, del square f by del y del x is same as doing the partial derivative with respect to y to the function del f del x. Okay, and this is also same as f of x. So sometimes this is written like f x of y because we are doing the partial derivative with respect to y to the function f of x. Or this is simply just f of xy. So now I think we have understood the definition of fxy and fyx. Okay, and not always these two are equal. So there are some theorems regarding that. The Euler's theorem, that when these two values are equal at particular point. So now first we're going to write the definition fyx at the point 0, 0. So f of x is nothing but doing the partial derivative with respect to x to the function f of y. So this will be limit h tends to 0, fy of h comma 0 minus fy of 0 comma 0 divided by h. So this is same as limit h tends to 0. Now here see that fy of h comma 0 is given by, fy of x comma 0 is given by x square. So fy of h comma 0 will be h square. And fy of 0 comma 0 is already given as 0. So this will be h square minus 0 divided by h. So this is nothing but limit h tends to 0 h, and this is 0. Similarly, fxy at 0 comma 0 is same as doing the partial derivative with respect to y to the function f of x. So it will be f of x 0 comma h minus fx 0 0 divided by h. Now we have seen that fx of 0 comma y is given by y. So this will be limit h tends to 0 h minus 0 divided by h, which is 1. Okay. So now fxy plus fyx at the point 0 0 is nothing but fxy at 0 comma 0 plus fyx at 0 comma 0. So fxy at 0 comma 0 is 1 and fyx at 0 comma 0 is 0. So the answer is 1. Okay. So hence fxy plus fyx at 0 comma 0 is 1. So this is our answer. So I hope this is clear. Yeah. So so you just write the partial derivative definition, the mixed partial derivative definition, the limit definition, and then you just put all the values, that is fxy 0 0 and fyx 0 0, so which is nothing but 1 plus 0. So the answer is 1. So this is very simple. So now we're going to go into the next part of this discussion session. So now we're going to write the definition of differentiability first. So differentiability. So differentiability is generally defined on open set. That means the point which belongs to an integral of a set. So that's why we will take the domain to be open here. So let D subset of R to be open. And let f is a function from D to R. Then f is differentiable at a point a comma b if there exists epsilon 1 equals to epsilon 1 of h comma k and epsilon 2 equals to epsilon 2 of h comma k, such that del f minus df equals to h epsilon 1 plus k epsilon 2, where epsilon 1 comma epsilon 2 tends to 0 as h comma k tends to 0 comma 0. So here del f is nothing but f of a plus h comma b plus k minus f of a comma b, and df is nothing but h fx of a comma b plus k fy of a comma b. So now this is just a basic definition of differentiability at a point a comma b. Okay. So now if the function is differentiable, then definitely both the partial derivative has to exist at the point a comma b. So by contrapositive, we can say that if one of the partial derivative, I mean with respect to x or y, do not exist at the point a comma b, then definitely the function is not differentiable. So and also equivalently, this definition is always not helpful to find out given a function is differentiable or not. So that's why equivalently we're gonna write a definition which will be helpful to find out given a function is differentiable or not. And the definition is given like this. So it's just kind of a theorem. So f is differentiable at a comma b if and only if limit h comma k tends to 0 0 del f minus tf divided by square root of h square plus k square is 0. If this definition hold, then we can say, I mean, if this limit is 0, then we can say the function is differentiable, and if this limit is not going to 0, then we can say the function is not differentiable. Now, this is a very good definition actually to check because we already know how to check limit of function of several variables. So that's why it will be helpful once we find out the values of the delta f and df. Then we can try to see if the limit goes to 0 or not. If it goes to 0, then the function will be differentiable. And if the limit do not go to 0, then the function will not be differentiable at the given point a comma b. So let us solve some questions, and then we can see what's going on, and we can understand the problem very nicely. Okay. So uh, so the question is given like this. So let f from R2 to R be defined as if xy equals to xy divided by x square plus y square to the power alpha. If x comma y is non-zero and 0 if x comma y is 0 comma 0. So then what is the value of value of alpha such that f will be differentiable at 0 comma 0. Okay. So now first we can try to check that what is the value of alpha such that the function is continuous at 0 comma 0. So first let us check the continuity, because if the function is not continuous, then it cannot be differentiable. So let us just find that what is the value of alpha first, then such that the function is continuous at 0 comma 0. And so here f of 0 comma 0 is 0. So first let us find the value of alpha such that f is continuous at 0, 0. So to become the function continuous at 0, 0, we need the epsilon delta definition. So this is nothing but xy divided by x square plus y square to the power alpha. Now this is same as mod x into mod y divided by x square plus y square to the power alpha, right? So now this is less equals to square root of x square plus y square into x square plus y square root of divided by x square plus y square to the power alpha. So this is because x square is less equals to x square plus y square and y square is less equals to x square plus y square. So mod x less equals to square root of x square plus y square and mod y is also less equals to square root of x square plus y square. So this will be less equals to x square plus y square to the power 1 minus alpha, correct? So now see that if so now we need x square plus y square to the power 1 minus alpha to be less than epsilon, right? So now if simply just 1 minus alpha become greater than 0 or so it depends on the definition. So if you want 0 less than square root of x square plus y square less than delta implies this. So then we need x square plus y square is equals to epsilon to the power alpha minus 1. Sorry. Epsilon to the power 1 by 1 minus alpha and then square root of x square plus y square is equals to epsilon to the power 1 by 2 into 1 minus alpha. So now we need delta to be epsilon by 1 to the power 2 into 1 minus alpha and we need 2 into 1 minus alpha to be greater than 0 or alpha to be less than 1, correct? So if alpha less than 1 and delta equals 2 epsilon by 1 to the power 2 into 1 minus alpha, then the above epsilon delta definition holds. So as long as alpha is less than 1, f is continuous at 0, 0. Okay. So now from here, can you say about differentiability that if alpha is less than 1, then f is also differentiable at 0, 0? That we don't know yet. So we have to find out using the definition. So now we'll find out the values of alpha for which the function is differentiable at 0, 0. Okay. So now we will find out the value of alpha such that f is differentiable at 0, 0. Okay. So what is the definition of differentiability? What was the equivalent definition of differentiability at the point 0, 0? So it was like this: limit h comma k tends to 0, 0. Okay, sorry, let me write in different color. Limit h comma k tends to 0, 0. Del f minus tf divided by square root of h square plus k square should be 0. Then we can say the function is differentiable at 0, 0. Now del f is nothing but f of h comma k minus f of 0, 0. So this is nothing but hk divided by, hk divided by h square plus k square to the power alpha, and df is nothing but hfx00 plus kfy00. Okay, so now first we have to find out the values of fx00. So this will be limit h tends to 0 f of h comma 0 minus f of 0, 0 divided by h, and this is simply 0. This is because f of h comma 0 is nothing but h times 0 by h square to the power alpha divided by h, and this is 0. Similarly, fy at 0, 0 is 0. So df equals to hfx00 plus kfy00 is 0. So now this definition is nothing but limit h comma k tends to 0, 0, hk divided by h square plus k square to the power alpha divided by square root of h square plus k square, and this is same as limit hk tends to 0, 0, hk divided by h square plus k square, this is k square to the power alpha plus half. Okay, so now we have to find out the values of values of alpha for which this limit is 0. So just take k to be h to be r cos theta and k to be r sin theta. Then h square plus k square is nothing but r square, and as hk tends to 0, 0, r tends to 0. So the definition changed to limit r tends to 0, r cos theta, r sin theta divided by r square to the power alpha plus half, and this is same as limit r tends to 0, r square cos theta sin theta divided by r to the power 2 alpha plus 1, and this is also same as limit r tends to 0, r to the power 2 minus 2 alpha minus 1 cos theta sin theta, and this is same as limit r tends to 0, r to the power 1 minus 2 alpha cos theta sin theta. So now see that to become this limit 0, we need r to the power 1 minus 2 alpha to go to 0 as r goes to 0. Now this will only happen when 1 minus 2 alpha is greater than 0, and this is implying alpha is less than half. So as long as alpha is less than half, f is differentiable at 0, 0. So yeah, I hope this question is clear now. This is just simply using the basic definition of differentiability, the equivalent definition of differentiability uh, at the point 0, 0. So we have solved two questions simultaneously. One to find out the values of alpha for which the function is continuous at 0, 0, and similarly the values of alpha for which the function is differentiable at 0, 0. Okay. So now we're gonna go to on to the next question. So this will be question number 7. Okay. So yeah. So the question is given as if z equals to sine of x plus y plus cos of x plus y, then find the value zx plus zy at 0, 0. Okay. So since here z is a function of two variables, or we can find the partial derivatives because both the function is differentiable. So it's a sum of two differentiable function which is differentiable. So zx is nothing but del z del x. So this will be same as cos of x plus y minus sine of x plus y, and zy is nothing but del z del y. So this will be also cos of x plus y minus sine of x plus y. Okay. So zx plus zy at 0, 0 will be 2 times cos of x plus y minus sine of x plus y, and this will be nothing but 2 times 1 minus 0, which is 2. So zx plus zy at 0, 0 is nothing but 2. So this is the answer. So yeah, I hope this is clear. Okay. So this is just using the partial derivative with respect to x and with respect to y. So since z is a function of two variable x and y, so the del z del x is nothing but partial derivative of x keeping the y constant. So the derivative of cos sine of x plus y is nothing but cos of x plus y. So this will be cos of x plus y, and then again the derivative of cos of x plus y is sine of x plus y. Similarly, also we can do the derivative with respect to y, keeping x as a constant variable. So here the derivative will be also cos of x plus y, and then negative of sine of x plus y. And then we just put the derivatives zx and zy in the definition, that is zx plus zy. And then this is nothing but 2 times cos of x plus y minus sine of x plus y. So now you just put the values of 0, 0, which is x comma y comma 0. I mean x and y both are 0. So this will be cos 1, and this will be sin 0. Sin 0 is 0 and cos 0 is 1. So this will be 2 times 1 minus 0, which is 2. So the answer is 2 here. Okay. So we're going to go to the next question. So I think this will be question number 8. So examine the differentiability of f at 0, 0. So f is given by xy divided by square root of x square plus y square, where xy is 0, 0 and 0 when xy is 0, 0. Okay. So this is a very important question, I think, and this question has been asked in many competitive exam. And so here we have to check the differentiability of the function f at the point 0, 0, where f of x comma is given by xy divided by square root of x square plus y square when xy is sorry, this will be not equals to 0, 0, and 0 when xy is 0, 0. So yeah, now we're gonna do the solution. So now before checking the differentiability at 0, 0, we'll check the continuity of the function at 0, 0, because if the function is not continuous, then it will not be differentiable, because differentiable functions are necessarily continuous. So our question is f continuous at 0, 0? Now, one thing to notice here that uh, f of 0, 0 is 0, and to check the continuity at 0, 0, uh, we need the epsilon delta definition. So we have to show that given epsilon greater than 0, there is delta greater than 0, such that modulus of fxy minus f00 is less than epsilon whenever this holds. Okay. So now since f of y 0, 0 is 0, so fxy minus f00, this is nothing but modulus of xy divided by square root of x square plus y square, and this is same as mod x mod y divided by square root of x square plus y square. So now see that x square is less equals to x square plus y square, and y square is less equals to x square plus y square. So mod x is less equals to square root of x square plus y square, and mod y is also less equals to square root of x square plus y square. Hence, modulus of fxy minus f of 0, 0 is less equals to square root of x square plus y square times square root of x square plus y square divided by square root of x square plus y square. So this is same as square root of x square plus y square. So just take delta equals to epsilon, then modulus of fxy minus f of 0, 0 is less than epsilon whenever this holds. So thus we can say f is continuous at 0, 0. Okay. So since using the epsilon delta definition, we have shown that given epsilon greater than 0, there is a delta, which is nothing but the epsilon itself. Then the function, then the definition of epsilon delta holds. So that means the function is continuous at 0, 0. So now we have to check the differentiability. Okay. So to check the differentiability, we have to show that limit hk tends to 0, 0, del f minus df divided by square root of h square plus k square is 0, where del f is nothing but f of h comma k minus f of 0, 0, and df is nothing but h fx 0, 0 plus k fy 0, 0. Correct. So now let us try to find what is fx 0, 0. So fx 0, 0 is nothing but limit h tends to 0, f of h comma 0 minus f of 0 comma 0 divided by h. So this is limit h tends to 0, h times 0 divided by h square plus 0 square divided by h. So this is nothing but 0. Similarly, fy 0, 0 is limit h tends to 0, f of 0 comma h minus f of 0 comma 0 divided by h. So this is same as limit h tends to 0, 0 times h divided by square root of 0 square plus h square divided by h. This is also 0. Correct? So df equals to 0 and delta f is nothing but f of h comma k. Okay. So now the definition of limit h k tends to 0, 0, del f minus df divided by square root of h square plus k square is same as limit h k tends to 0, 0, and del f is nothing but hk times, because del f is f of h comma k, so this will be hk times hk times what was the function? So yeah, square root of h square plus k square divided by square root of h square plus k square. So this is nothing but limit h comma k tends to 0, 0, hk divided by h square plus k square. Now to become the function differentiable at 0, 0, this limit should go to 0. But I think we all can guess at this point that this limit at the point 0, 0 does not exist. This is because choose the path k equals to mh, where m is a real number. Then this is nothing but limit h tends to 0, h time mh divided by h square plus mh square. So this will be limit h tends to 0, mh square divided by h square time 1 plus m square. So this is nothing but m divided by 1 plus m square. So now if we just vary the values of m, then we are getting different limit of this function hk divided by h square plus k square. So that means the limit of the function at the point 0, 0 do not exist, because if it exists, it should be unique. But here we are getting different type of limits, different values of limit. So that means limit h comma k tends to 0, 0, hk divided by h square plus k square does not exist. Okay, so this implies that f is not differentiable at 0, 0. Okay, so since this limit does not exist and do not converge to 0, then by this that equivalent definition of differentiability, we can say that the function is not differentiable at 0, 0. Now this thing also we can check using polar coordinate, that this limit does not exist. So this we can check using polar coordinate. So what are you gonna do? Take h equals to r cos theta and k equals to r sin theta. Then h square plus k square is r square, and as h comma k tends to 0, 0, r tends to 0. So limit h comma k tends to 0, 0, hk divided by h square plus k square is nothing but limit r tends to 0, r square cos theta sin theta divided by r square cos square theta is r square sin square theta, right? And this is same as limit r tends to 0, r square cos theta sin theta divided by r square time cos square theta plus sin square theta. And this is same as cos theta sin theta. So now here we also can see that the limit of the function is, so the limit of this function hk divide by square root of, sorry, divided by h square plus k square, depending on the values of theta here, because for different values of theta we'll get different values of cos theta and sin theta, and we'll get several values, even infinite values of limit, and that should not happen, right? Limit should be always unique. So by using polar coordinate also we can prove that this is not going to 0, and hence f is not differentiable at 0, 0. Okay, so I hope this is clear now. So if this is clear, then we're gonna go into the next question. So this was, I think, question number 8. Yeah, let me see. Yeah, this was question number 8. So now we're gonna do question number 9. Okay. So if w equals to x plus y by z, where x equals to cos square of t, y equals to sin square of t, and z equals to 1 by t, then the value of dw by dt at t equals to 3 is, so yeah, so here w is a function given of with three independent variables x, y, and z, and x is a function of the variable t, y is also a variable of t, function of variable t, and z is also a function of variable t. Then they are asking us to do the derivative of w with respect to t and find out the values at the point t equals to 3. Now this is a question from the chain rule. So here we can just see that w is a function of three variables x, y, and z, and both x, y, z are functions of the variable t. Correct. To do the derivative of w with respect to the variable t, so first we have to go to the x variable and then to t variable. Similarly to y variable, then to t variable, and also similarly to z and then to t. Okay. So this is how we have to do the derivative. So then z and then to t. Okay. So this is solution. So dw by dt will be nothing but del w by del x into del x del t. So through the first variable x, and then again del w del y into del y del t, and then again del w del z into del z del t. So now we have to find out all the values, I mean all the partial derivatives here. So now see that del w del x is nothing but del x of x plus y by z, and this is nothing but 1 by z. Similarly, del w by del y is also 1 by z, and del w by del z is nothing but minus of x plus y divided by z square. Okay, and del x del t is nothing but because x was sine square of t, sorry, cos square of t, so it will be 2 cos t, and the derivative of cos t is minus sine t, so it will be minus sine 2t. Similarly, del y del t will be 2 sine t cos t, so this is also sine 2t, and del z del t will be nothing but, since z is 1 by t, so del z del t will be minus 1 by t square. So now we have to substitute all this partial derivative into dw by dt, the definition of dw by dt. So dw by dt is nothing but, so first it was del w del x and del x del t, and del w del x is nothing but 1 by z. So 1 by z time, what is del x del t? So del x del t is minus sine of 2t. So minus sine of 2t. Similarly, del w del y is also 1 by z, and this is sine 2t. So 1 by z sine of 2t, and then del z del t into sorry, del w del z into del z del t. So it will be minus of z square into minus 1 by t square. So now see that these two get cancelled out. So this is x plus y by z square t square. Okay, so now we can put the values of x, y, and z. So x was, I think, cos square of t. Yeah, x was cos square of t and y was sin square of t. So this will be cos square of t plus sin square of t divided by 1 by t square into t square, because z was 1 by t. So this gets cancelled out. So this is cos square of t plus sin square of t, and which is 1. So dw by dt is 1. So this will imply that dw by dt at t equals to 3 is also 1. Because for any values of t, the derivative with respect to the variable t is nothing but 1. So at the particular point t equals to 3, it will be also 1. So hence dw by dt at the value t equals to 3 is 1. So this is our final answer. So I hope this is clear. So if there is any doubt, so kindly go through the answer again, and also see the video again. And if there is doubt again, then just tell me in the next class. Okay. Okay. So now we'll go to the next question. This is question number 10. So yeah, the question is given like this. Let z equals to f of x comma y, where x equals to e to the power u cos v, and y equals to e to the power u sin v. If y times del z del u plus x time del z del v equals to alpha time del z del y, then what is the value of alpha? Okay. So here z is a function of two variables x and y, and both x and y are a function of another two variables u and v. So to do the derivative of z with respect to u, first we have to go to x and then to u, similarly to y and then to u. And to do the partial derivative with respect to v, we have to go from x z to x and then x to b, similarly z to y and y to v. So that's how we do the partial derivative when the function is a chain of functions, right? Because z is a function of xy and xy is a function of uv. So ultimately z is a function of xy and then xy is a function of uv and z is a function of uv. So first we're going to find out the derivative of z with respect to u, and del z del u is nothing but uh, del z del x into del x del u plus del z del y into del y del u. Similarly, del z del v is same as del z del x into del x del v plus del z del y into del y del v. Okay. So now here x is given as e to the power u cos b and y is given as e to the power u sin b. So del x del u is nothing but e to the power u cos b and del x del v is nothing but minus e to the power u sin b. Similarly, del y del u is e to the power u sin b and del y del v is e to the power u cos b. Okay, so now we have to put all the values of del z del x and I mean del x del u del y del v del x del v and del y del u in the equation. So it was given that y times, so yeah, so del z del u is nothing but del z del x into del x del u, which is e to the power u cos b plus del z del y into del y del v, which is e to the power u sin b. So this is, since e to the power u cos b is x and e to the power e to the power u sin b is y, so this will be x zx plus y zy. Similarly, del z del v will be del z del x into del x del v, which is minus e to the power u sin v plus del z del y into del y del v, so which is e to the power u cos b. So now since e to the power u sin v is y and e to the power u cos b is x, so this will be minus of y times zx plus x times zy. Now given that it was given that y zu plus x zb equals to alpha zy. Y del z del u plus x del z del v equals to alpha del z del y or alpha zy. So this is implying y times z of u is nothing but x zx plus y zy plus x times this is minus y zx plus x zy, and this is same as alpha zy. So this is implying. So now just collect the coefficient of zx and zy. So it will be y of x minus x of y plus zy. It will be y squared plus x squared, and this is same as alpha zy. Now this got cancelled out. So this is implying zy time x squared plus y squared equals to alpha zy, and this is implying that alpha equals to x squared plus y squared. So this will be our answer. Hence, alpha equals to x squared plus y squared. Okay. So yeah. Okay. So now we're going to go to the next question, which is question number 11. So now this question I will be solving that was asked in IT Jam 2025. So this was a 2 marks question from MSQ, and the question is given like this. So this was IT Jam 2025, and this was MSQ 2 marks question. So f is a function from R2 to R defined by f of x comma y equals to x square plus sin x into y square divided by x square plus y square when xy is non-zero and 0 when xy is 0, 0, 0. Then which of the following is less or true? So the first option is limit xy tends to 0, 0 if xy exists and equal to 1. Next option is exists and so next option is limit xy tends to 0, 0 if xy exists and equals to 0. And the next option is f is differentiable at 0, 0. And the fourth option is f is not differentiable at 0, 0. Okay. So this type of questions are asked in IIT JAM exam. So IIT JAM is a exam where after graduation you can give the exam and come to IITs for doing masters. So you can find out more in the website, in the official websites of IIT JAM. So now this is a very interesting question. I mean, this is not truly straightforward to show that the limit exists. I mean, limit xy tends to 0, 0 if xy exists and equals to some value. So now our guess is that it can go to 0 because you see in the numerator that the dimension, I mean the power of the sum of power of both x and y are much higher than the denominator, right? So we are expecting or we are claiming. So we are claiming that uh, limit xy tends to 0, 0, f of xy is 0. So this is our claim. Now to prove that, we have to show that f of xy minus 0 is less than epsilon whenever 0 less than a square root of x square plus y square is less than delta. Now modulus of xy f xy minus 0, this is nothing but modulus of x square plus sine of x times y square divided by x square plus y square. Okay. So now see that y square is less equals to x square plus y square. So this is implying y square divided by x square plus y square is less equals to 1. So modulus of fxy minus 0 will be less equals to modulus of x square plus sine x. Since y square divided by x square plus y square is less equals to 1. And so this will be less equals to x square plus modulus of sine x using triangle inequality. And this is also same as x square plus mod x, as modulus of sine x is less equals to mod x for all real number x. Correct. So now we have to show that this is less than epsilon whenever square root of x square plus y square is less than delta. So now see that x square is less equals to x square plus y square and mod x less equals to square root of x square plus y square. So fxy minus 0 will be less equals to x square plus y square plus square root of x square plus y square. So now from here we have to show that this term, the left hand term here is less than epsilon whenever square root of x square plus y square is less than delta. So given epsilon greater than 0, we are choosing delta as minimum of 1 comma epsilon by 2. So then delta is less equals to 1 and delta square is less equals to delta, right? So modulus of fxy minus 0 is less equals to delta square plus delta. So now since delta square is less equals to delta, so it will be 2 delta. Now from here delta is less equals to epsilon and 2, and this is implying 2 delta is less equals to epsilon, and this is less equals to epsilon. Hence, even epsilon greater than 0, if we choose delta equals to minimum of 1 comma epsilon by 2, then 0 less than square root of x square plus y square less than delta will imply fxy minus 0 less than epsilon. And this is implying that limit xy tends to 0, 0, fxy is 0. So that means our second option is correct. Now, since this is an MSQ type question, so we have to check the all other options because this is not an MCQ. If it's an MCQ, then one option, if one option is correct, then you can just tick that option. But since this is an MSQ, we have to check the other options like C and D because A cannot hold because since the limit is 0 only. So now we have to check the differentiability. Okay, so now one thing to notice here is that f of 0, 0 is 0. So this implies the function is continuous because you can do the same thing that epsilon delta definition you can go through again and show that modulus of fxy minus f of 0, 0 will be less than epsilon whenever 0 less than square root of x square plus y square is less than delta. So this will imply that f is continuous at 0, 0. Okay, so to check the differentiability, we have to go through the definition, the equivalent definition of differentiability. Okay. So now we have to check the differentiability at 0, 0. Correct? So what was the definition of differentiability at 0, 0? So it says that if h comma k tends to 0, 0, del f minus tf divided by square root of h square plus k square is 0, then f is differentiable at 0, 0. So we have to check this. So del f is nothing but f of hk minus f of 0, 0. So this is same as f of h comma k, and df is nothing but hfx 0, 0 plus kfi 0, 0. So now fx 0, 0 is nothing but limit t tends to 0, f of t comma 0 minus f of 0 comma 0 divided by t, and this is same as limit t tends to 0, t square plus sine t multiplied by 0 divided by t square divided by t, and this is 0. Similarly, fy at 0, 0 is limit t tends to 0, f of 0, t minus f of 0, 0 by t, and this is same as limit t tends to 0, 0 square plus sine 0 into t square divided by t square by t, and this is 0. So fx 0, 0 equals to fy 0, 0 equals to 0. Correct? So this implying that tf equals to 0. So now our definition, del f minus tf divided by square root of h square plus k square uh, will change into limit h comma k tends to 0, 0 h square plus sine h into k square divided by h square plus k square into square root of h square plus k square, and this is same as limit h k tends to 0, 0 h square plus sine h into k square divided by h square plus k square to the power 3 by 2. Okay, so now we'll show that this limit does not exist. Now if we just show that this limit does not exist, then we can clearly say that this limit is not going to 0, and hence the function is not differentiable at 0, 0. Because if the function is differentiable at 0, 0, then this limit should go to 0. So for that, we're going to choose this path, k equals to h, and then we can show that limit h comma k tends to 0, 0, or maybe we can take k equals to mh and try to see what's going on, and then limit h tends to 0, h square plus sine of h into m square h square divided by h square plus m square h square to the power 3 by 2, and this is same as limit h tends to 0, hq time h plus sine sorry m square h square plus sine h divided by hq time 1 plus m square to the power 3 by 2. So I think this will be okay. So this will be limit h tends to 0, m square time h square plus sine h divided by h time 1 plus m square to the power 3 by 2. So this will be limit h tends to 0, m square divided by 1 plus m square to the power 3 by 2 into h plus limit h tends to 0, m square by 1 plus m square to the power 3 by 2 sine h by h. Okay. Now this limit is 0, and this limit is m square divided by 1 plus m square to the power 3 by 2. So this is m square time 1 plus m square 3 by 3 by 2. So clearly we can see from here that for different values of m, we'll get different values of limit. So this limit does not exist, correct? Hence, so from here we can say that the limit does not exist. And so f is not differentiable at 0, 0. Okay. So option B and option D are correct. Okay. So now we're gonna go on to the next question, which is question number 12. Okay. So that the following function is not differentiable at 0, 0. So we have to show that this function is not differentiable at 0, 0. The function is given by x sine 1 by x plus y sine 1 by x when xy is non-zero and 0 when xy is 0. Okay. Okay. So to check the differentiability, first we're going to check the continuity, if the function is continuous at 0, 0 or not. And to do so, we're going to use the epsilon delta definition. So our first goal is to check whether f is continuous at 0, 0. Okay. So that means we have to show that fxy minus f of 0, 0 will be less than epsilon whenever 0 less than square root of x square plus y square less than delta. Correct. Now here f of 0, 0 is 0. Correct. So f of xy minus f of 0, 0 will be nothing but x sine 1 by y plus y sine y sine 1 by x. So by triangle inequality, this will be less equals to mod x sine 1 by y plus mod y sine 1 by x. And this is less equals to mod x mod sine 1 by y plus mod y mod sine 1 by x. And this is less equals to mod x plus mod y, as modulus of sine 1 by y less equals to 1 and modulus of 1 sine 1 by x is also less equals to 1. And we already know that mod x is less equals to square root of x square plus y square. Mod y is also less equals to square root of x square plus y square. Hence, modulus of fxy minus f of 0, 0 less equals to 2 times square root of x square plus y square. To show that fxy minus f of 0, 0 is less than epsilon, we need 2 times square root of x square plus y square less than epsilon, and this will imply, okay, let me write correctly, 2 times square root of x square plus y square less than epsilon, and this will imply x square plus y square root of x square plus y square less than epsilon by 2. So just take delta equals to epsilon by 2, then the definition hold. Hence, f is continuous at 0, 0. Okay. So now we have to check whether the function is differentiable at 0, 0 or not. Okay. And now we're gonna go with the basic definition of differentiability. That is, it was del f equals to df plus h epsilon 1 plus k epsilon 2, where epsilon 1 comma epsilon 2 tends to 0 as h comma k tends to 0, 0. And del f is nothing but f of hk minus f of 0, 0. So this is just f of hk, and we have to show that df of f is nothing but hfx 0, 0 plus kfi 0, 0. Okay, and fx 0, 0 is nothing but limit h tends to 0, f of h comma 0 minus f of 0 comma 0 by h. So this will be limit h tends to 0. Uh, so f of h comma 0 will be 0 minus 0 divided by h. So this will be 0 because h times 0 is 0. So since xy is 0, so it will be 0. Similarly, fy 0, 0 will be also 0. Hence, df is 0. Okay, so delta f is nothing but h epsilon 1 plus k epsilon 2. So that means h sine 1 by k plus k sine 1 by h equals to h epsilon 1 plus k epsilon 2. Okay. So now we have to show that this equality holds when epsilon 2 when hk tends to 0, 0, then epsilon 1 epsilon 2 tends to 0. So now just choose the path k equals to h. So then it will be 2h sine 1 by h equals to h times epsilon 1 plus epsilon 2. Okay, so then as h tends to 0, then LHS imply that sine 1 by h tends to 0, which is not possible, as limit h tends to 0, sine 1 by h does not exist. Hence, f is not differentiable at 0, 0. So this function is continuous at 0, 0, but it's not differentiable at 0, 0, although both the partial derivative exist at 0, 0. Correct? So yeah, I hope this is clear. Okay. So then we're gonna go to the next question. So that fxy equals to square root of modulus of xy is not differentiable at 0, 0. Okay. So first we'll show that the function is continuous at 0, 0, and then we'll show that the function is not differentiable at 0, 0. Okay. So so clearly we can see that f of 0, 0 is 0. Then f of x, y minus f of 0, 0 is nothing but modulus of square root of modulus of xy, and this is less equals to square root of mod x into mod y, and this will be less equals to square root of x square plus y square into square root of x square plus y square, as mod x less equals to square root of x square plus y square, and mod y also less equals to square root of x square plus y square. So this is less equals to square root of x square plus y square. So now take delta equals to epsilon, then modulus of fxy minus f of 0, 0 less than epsilon holds whenever 0 less than square root of x square plus y square less than delta. So this implies that f is continuous at 0, 0. Okay. So now we have to check whether the function is differentiable at 0, 0 or not. And before doing so, we have to find out the partial derivative at the point x and y. I mean at the point 0, 0 with respect to x and y. Okay. So fx 0, 0 is nothing but limit h tends to 0 f of h comma 0 minus f of 0, 0 divided by h, and this is nothing but limit h tends to 0, and f of h comma 0 is nothing but modulus of h times 0 minus 0 divided by h, and so this is 0. Similarly, uh, limit sorry fy of 0, 0 is limit h tends to 0 f of 0, h minus f of 0, 0 divided by h, and this is also 0. Okay. So by the basic definition of differentiability, TLF minus TF should be H epsilon 1 plus K epsilon 2. And here TF is 0. So F of HK minus F of 0, 0 is H epsilon 1 plus K epsilon 2. And this is nothing but square root of modulus of HK equals to H epsilon 1 plus K epsilon 2. So now we have to show that this equality holds when epsilon, epsilon 2, epsilon 1, epsilon 2 tends to 0 as h comma k tends to 0 comma 0. So now just take the path k equals to h, then this is nothing but modulus of uh, square root of modulus of h square equals to h epsilon 1 plus k epsilon 2, sorry, h epsilon 2. And this is same as modulus of h equals to h time epsilon 1 plus epsilon 2, correct? So from here, we can say that as h tends to 0, epsilon 1 plus epsilon 2 does not tends to 0. Hence, the function f is not differentiable at 0, 0. Okay. So yeah, I think this is clear. So first, we have just shown the function is continuous at 0, 0. Then we found out the partial derivative with respect to x and y at the point 0, 0. And then using the definition of differentiability, we showed that the function is not differentiable at the origin. So now we're gonna give a theorem. This is an important theorem. This is called the sufficient condition for differentiability. So yeah, I'll take a new page. So this is called sufficient conditions for differentiability. Okay, so now what it says. So it says that suppose fx of xy and fy of xy exist in an open neighborhood containing a comma b and both the function are continuous at a comma b. Then f is differentiable at a comma b. So this is just a sufficient condition. So it says that if both the partial derivative with respect to x and y exist in an open neighborhood of a comma b. So if there is a neighborhood of a comma b where both the partial derivative exist and both the functions are continuous, both the fx and fy are continuous at a comma b, then the function must be differentiable at a comma b. Now, not only that, we can say more, and we can give another corollary, and it says that if the above theorem holds, I mean, this above theorem still holds if fy is continuous and fx just exists at a comma b. So the above theorem is still true if y is continuous and fx exists at a comma b. Okay, so this is called sufficient condition for differentiability. Okay, so yeah, I'm gonna write also another uh, another definition, which is called directional derivative, and this is also equally important. I don't know if this was taught in the week class or not. I mean, in the second week or not. But this is, I think, equally important. So that's why I'm just giving the definition and some examples. So it's called directional derivative. Because sometimes questions comes from this directional derivative, especially in GATE and IT JAM exam. So let P equals to P1, P2, P any unit vector then the directional derivative of fxy at a comma b in the direction p is, so this is denoted like this, dp f of a comma b, and this is limit s tends to 0 f of a plus sp1 comma p plus sp2 minus f of a comma b divided by s. Okay, so this is called directional derivative. So unit vector means p1 square plus p2 square is 1. So let me write here clearly. So p is unit vector implies p1 square plus p2 square is 1. Okay. So yeah, let us give an example first. So take fxy equals to x square plus y square at the point 1 comma 2 in the direction u equals to 1 by root 2 comma 1 by root 2. Okay, so now we have to find du f of 1 comma 2. So this is limit s tends to 0 f of 1 plus s by root 2 comma 2 plus s by root 2 minus f of 1 comma 2 divided by s. So this will be limit s tends to 0, and this is nothing but 1 plus s by root 2 whole square plus 1 plus s by root 2 into 2 plus s by root 2 minus this will be, so if you put 1 and 2, then it will be 1 plus 2, which is 3, and This is divided by s, and this will be limit s tends to 0, 1 plus 2 s by root 2 plus s square by 2 plus 2 plus s square by 2 plus 3s by root 2 divided by s, and minus 3 also. Okay, so this is limit s tends to 0. Now this 3 got cancelled out here. So this will be root 2s plus s square by 2. So s square by 2, s square by 2 will be s square plus 3s by root 2 divided by s. So this will be limit s tends to 0, root 2 plus s plus 3 by root 2. So this is root 2 plus 3 by root 2. Okay. So that should be 2 and 3, 5 divided by root 2. Sorry, this is root 2. So this is the answer. So du f at 1 comma 2 is 5 divided by root 2. Okay. So now one more thing to notice here is that so for example, dp f of a comma b is nothing but limit s tends to 0, f of a plus sp1 comma b plus sp2 minus f of a comma b divided by s, where p is p1 p2. So now if you just take the direction and p1 square plus p2 square is 1. So if you just take p to be 1 comma 0, that means the direction is nothing but the x-axis. Then something magic happens. So then we can show that the direction derivative is nothing but the partial derivative of the point a comma b in the x direction. So in this case, dp at a comma b, this is limit s tends to 0. So this will be so since p is this p1 is 1 and p2 is 0. So this will be f of a plus s comma b, since p2 is 0, minus f of a comma b divided by s, and this is nothing but fx at the point a comma b. Similarly, if you take p to be 0 comma 1, then dp, so this will be dpf, then dpf of a comma b is nothing but fy of a comma b. So then we get the partial derivative in the y direction, correct? So if you just take p to be the y-axis, I mean the y direction, then the directional derivative is nothing but the partial derivative with respect to the variable y. Okay, so these are the two things I wanted to explain. I think these are very important, and there are also many lemmas. For example, if this is another theorem, if f is differentiable, then so then you can calculate this directional derivative by just taking the gradient at the point a comma b and then doing the dot product with p. So then this will be our directional derivative.